Electromagnetic radiation includes radio waves, microwaves that we use for our cell phones, visible light, X-rays, cosmic rays. It's a whole spectrum. Here's a nice representation of the electromagnetic spectrum that I Googled. On this side you have the longest waves.
Check out this info.
But also the lowest energy. On the right hand side you have the shortest waves but the highest energy. And then here you have some idea of the scale of these waves. And visible light is just a tiny fraction of the spectrum in the very center. Let's explore some of the common characteristics that this electromagnetic radiation has. Let's say I have a wave traveling from left to right at some speed, c. The peaks are the crests of the wave. The troughs, well, they're the opposite of peaks. The distance between one peak and the next is called the wavelength, symbolized by lambda, which is a Greek letter. It looks like an upside down Y. Since lambda is a measure of distance, we'll measure it in meters. Next is the frequency. We symbolize it with nu, which kind of looks like a drunk V. Now you can't draw the frequency directly on a wave, but if the frequency is the number of times a wave passes through a certain point per second, that is the number of waves passed through a point in a second. So that's equal to the speed, right, because the faster it's going, the higher the frequency, divided by the wavelength. So a longer wavelength means a shorter frequency. In other words, frequency and wavelength are inversely proportional. And since, let's see, c, the speed is meters per second, and the wavelength is in meters, then the frequency nu is just in inverse seconds, or 1/, seconds. Right, because meters per seconds divided by meters, the meters goes away, and you just have 1/, seconds. Now, there are some observations that we have made that prove that electromagnetic radiation has wave properties. In other words, it travels in waves. Waves interfere with each other. If you've ever looked at ripples in a pond when you throw two rocks in at different places, you can see the wave fronts interfering with each other. There's two types of interference. So first look in this box. So say we have two waves, the red wave and the blue wave, that are in phase. That is, they're lined up so that the peak of the blue wave and the peak of the red wave are in the same horizontal position, and the trough of each is in the same horizontal position. These two will interfere constructively. They'll add up so that you get a new wave whose total height is equal to the sum. Right? This is constructive interference because these waves are in phase. On the other hand, if you look in this box, these two waves are out of phase. That is, where we see a peak in the blue wave corresponds to a trough in the red wave. Where we see a trough in the blue wave corresponds to a peak in the red wave. And when you sum that up, the total amplitude is 0. This is called destructive interference. Right? So as far as electromagnetic radiation is concerned, the taller the wave, the more intense the radiation. Now comes the phenomenon of diffraction. When you pass a horizontal wavefront through a slit, the wavefront is diffracted, and now it becomes a circular wavefront. If we have two slits, then the two circular wavefronts interfere with each other, and you get an alternating pattern of constructive and destructive interference. Now, if you shine visible light, or a single wavelength of a visible light, like a laser, through a pair of slits that are the right size, you see this double slit diffraction pattern. Really, it's an alternate pattern of light and dark. Here's another example of a diffraction pattern. So, because we can see diffraction patterns, what can we conclude? We can conclude that light is a wave. But is light only a wave? Well, have you ever gotten a sunburn? If you have, you know that light interacts with matter. So here I am with purple light at a relatively low intensity of 23%, and it is causing the ejection of electrons from the metal surface. That's because the light imparts enough energy to those electrons that they can jump across the gap. Now, if I increase the intensity of the light, that increases the number of electrons that are jumping across the gap per second. Okay, that seems reasonable. So, does this work for any color of light? Let me put the intensity back down and let's try blue light. Sure enough, I still have electrons jumping across the gap. And if I turn up the intensity, I get more of them. Turn it back down. Now if we compare this with the purple light makes the electrons come out faster. The blue light, the electrons are slower. Okay, let's go to green. We're still getting electrons, but they are still slower. We move to a longer wavelength of green. Hey, we're almost yellow, look, but, right, so this is our almost yellow light hitting the metal surface, but no electrons. What if I jack up the intensity? Still no electrons. Well, let's shorten the wavelength again. Aha! At 530 nanometers, now we're seeing it, but at 540, no electrons. Oh, it's hard to move this thing. At 527, we're seeing some. At 532, yep, we still got some. At 535, we're still good. At 538, we're still seeing electrons, but now they're moving very slowly. At 541, no more. So between 538 and 541, no more electrons, even at the highest intensity. So that's kind of a head scratcher right there. Let's summarize our observations. Shorter wavelength means faster electrons, but above 538 nanometers, we get no electrons. It actually took Einstein to figure this out. Einstein postulated that if the continuous wave model of light was complete, then more intense light, with a wavelength lambda, greater than 538 nanometers would lead to electrons. But Einstein was so smart he was able to come up with an explanation for this. Einstein's explanation is that light is both a wave and a particle at the same time. These wave particles he called photons. And he said that one electron interacts with one photon. Furthermore, the energy of a photon depends only on its frequency. So it's a constant h times nu, the frequency. And since frequency is equal to c over lambda, then energy equals hc over lambda, where h is Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. For this to work, you have to convert your wavelength to meters. So you recall from the photoelectric demonstration that the longest wavelength of light that would cause electrons to be ejected from the metal surface was 538 nanometers. If we convert that to meters, we have 10 to the negative 9th meters for 1 nanometer. And when we do that conversion, we get 5.38 times 10 to the negative 7th meters. So the energy of one of these photons equals hc over 5.38 times 10 to the negative 7th meters. Plugging in the numbers, here's h, 6.626 times 10 to the negative 34 joules times second. Here's c, 3 times 10 to the 8th meters per second. That's the speed of light. It goes 300 million meters per second. Holy cow, that's fast. And we divide all that by 5.38 times 10 to the negative 7th meters. And when I plug that into my calculator, well, you plug it into your calculator and pause the video while you do that, and then you can press play once you've done the calculation and see if you get the same thing I got. So doing this calculation, I get 3.69 times 10 to the negative 7, times 10 to the negative 19th joules. All visible photons are going to be something times 10 to the negative 19th joules. Now, if you got something different, it's probably because you didn't do it right in your calculator. You want to use the exponent button or EE instead of typing in times 10 caret blah blah blah. Now try a calculation of your own. What's the energy of a photon at 541 nanometers? Remember to convert that to meters and use the equation E equals hc over lambda. Right? And the meters is the lambda. This is what your calculation should look like. H is 6.626 times 10 to the negative 34th joules times second. C is 3.00 times 10 to the 8th meters per second. And lambda, the wavelength that was given in nanometers, converts to 5.41 times 10 to the negative 7th meters. And when I punch it all into my calculator, I get 3.67 times 10 to the negative 19th joules.